by CRO when I joined ISI way back in the early 60s, 62 to be precise. And he asked me one question which I still remember: how do you estimate the output of wheat for the entire country? So I blabbered something, and then he asked me, who told you the story? And he also asked what specialization you had. I said I had econometrics. Then I told him my professor told me. That's my answer. He just laughed and then he just left it. After a few weeks later, see, I used to go always with my good friend T.S. Raghavan, who also was with ISI, because we studied together from the high school, and we met Professor Rao on the way in the third floor of the RTS, and he asked each one of us what is the field in which you want to do research. I said decision theory. I don't know much about that, but I just said it. And my friend said multivariate analysis. Then he suggested, why don't you try your hand in game theory? That's how I started working on it. So that is, he is the first one to tell us to do something in game theory. Then we started reading some papers and just started doing something, and then we gave talks, and Professor Basu was also very helpful in that connection, because we had difficulty in understanding some of the results in convex sets. And we took a book which is a very strange book by, maybe you might not have heard the title of that book, or even it is written by Eggleston, which is a very short book, but not, I mean, it's difficult to, read that book. But Basu used to explain many of the ideas in that book, and later we found out a very nice book by a French person who visited ISI, who really initiated the many students who work in graph theory, Claude Bush. So we read his book, and that's how we started working in game theory. Okay. Of course, I used to correspond with Lloyd Shapley in connection with the game theory, because he is the father of statistics during my time, and he used to help me a lot. He is another person who used to guide us. All right. So let me talk about something which one of the students at Chennai Mathematical Institute wrote as a master's thesis. I am going to explain the problem. It's a very, it looks like a simple problem, but later we found out that we don't have a complete answer to this question. In fact, I am going to mention 3 or 4 papers which are relevant to this topic. 2 of the papers were written by a well-known mathematician from the University of Chicago, Irving Kaplansky. His main field is something else, not game theory. He wrote one paper way back in the 40s and another paper 50 years later connecting with that. See, von Neumann proved a very remarkable result about 90 years back, the so-called minimax theorem. I will write down what it is, everything. Professor Kaplansky was able to classify a special class of matrix games which can be identified as completely mixed matrix game. See, in any, let me start with a simple example of a game. Maybe you might have played this game also. There are 2 players, each player has 3 objects in their hands. The 3 objects you can visualize as paper, scissor and rock, paper, scissor. Let me write it. Here the rock, paper, scissor, rock, paper, scissor. Here I am going to write some numbers. See, each one has to produce one object simultaneously. That is, what one produces is not known to the other before they do it. Okay? So that's these are games with imperfect information, unlike chess. So suppose both produce rock simultaneously, I get 0. This payoff matrix I am going to write with reference to mine. If it is positive, I get that much money from my opponent. If it is negative, I have to pay him. That is the interpretation. Okay. Suppose I produce rock and he produces paper. Paper can fold the rock, that means I lose. So I lose 1 unit of money. I just write some number. Okay. Suppose I produce rock and E produces scissor. Rock can spoil the scissor, so I get 2 units of money. Okay. So, here this is going to be 1 and minus 2, you can check it. This is 0. If I produce paper and he or she produces scissors, scissor can cut the paper, that means I lose. So, I lose some, now I just write some number, minus 3, 3, 0. So, this is a typical example of a matrix game which was analyzed by von Neumann. So, how do you play this game if you play between you and your opponent several times? What is your strategy? Obviously, you can't produce every time rock, then I know you are producing that, then I will produce paper, I will get 1 unit. So, you have to mix up. So, here the best strategy is the following. I am going to write down the strategy for each player. This is 1 by 6, 3 by 6, 2 by 6. So, this is the best strategy for each player. That is, if you play 60 times this game, 30 times you use rock, 20 times you use paper and 10 times you use pen. But of course, this you should do it in a randomized fashion. Okay. And this way, what do I get? If you multiply this, I get 0, 0, 0. So, in other words, in this game both players will be using the same strategy. There is no other way you can play this game optimally. There is only one optimal for each player, namely the one which I have given, that you can verify. Such class of games are called completely mixed matrix games. I mean, this is the definition of a matrix game. Let me write it here. Call a strategy, by that I mean a probability vector x, completely mixed if xi is positive for all I equal to 1 to m. Assume that there are the matrix, I mean here I have a 3 by 3 matrix. So, here strategy is called completely mixed if it is of this form. That is, every coordinate of the probability vector should be positive. Such a strategy is called completely mixed. The game is called completely mixed. I mean, this particular game which I denote by A is called completely mixed if every optimal is completely mixed. Here, if I do anything else, I will be punished. Similarly, if you do anything else, you will be punished. I mean, we are assuming that both are playing rationally with that assertion. So, this game is a completely mixed game because you can't find any other way of play. For example, suppose I play half 0. If I use this, I am going to multiply with this row. So, what I get is half into 1, half into minus. So, half plus half minus 2, which is equal to minus half. Here it is minus half plus, so it is minus half plus 3 by 2, which is 1. Similarly, here 2 minus, so it is minus half. So, you may lose because the other player will use these two, so that you are punished, you will be giving more. Because this is that is, if you chooses the first column, you will lose minus half. If you chooses the third column, then also you lose. Here 0 is the best thing, that is, by playing optimally, you are not going to lose more than 0. If you if you don't play optimally, you will be giving money to your opponent. So, that is the interpretation. See, the von Neumann's minimax theorem says the following. Let me write it here. This is the first result in game theory. That is, I have a matrix which is called the payoff matrix. With every such matrix, you can associate there exists a real number V and a strategy. Assume that the rows are chosen by player 1 and columns are chosen by player 2. I will assume that the person who chooses the row is a maximizer and the person who chooses the column is a minimizer, then there are optimal strategies for player 1, which is of the form Aij xi naught I equal to 1 to m, which will give him V at least for all j, no matter what the other player does. And similarly, the minimizer has a strategy yj naught j equal to 1 to n, which is less than or equal to V for all I. The interpretation is very simple. By playing this, I will get at least V. By playing this, player 2 restrict player 1's average income to at most V. This V is called the value of the game, and in this example, the value of the game is 0, and the optimal strategy y naught is this, and the same strategy is also optimal for player 1, who is the maximizer. So, that is the interpretation. So, Kaplansky gives a set of nice, necessary and sufficient conditions under which each player will have a strategy. If he plays optimally, will use every one of his pure choices with positive probability, and same goes for the other player. Such games are completely mixed. His theorem is very nice, so let me state the result of Kaplansky. 1945, Annals of Mathematics. I am going to assume the value of the game is 0. With that assumption, game A associated with the payoff matrix is completely mixed if and only if the number of rows equal to number of columns, the rank of the matrix A is equal to n minus 1. The third condition is all the cofactors of the given matrix. Aij is the cofactor of the ijth element of A, which is nothing but minus 1 power I plus j multiplied by the determinantal value of leaving out the ith row and the jth column from the given matrix. So, this all the cofactors are either positive, all of them are positive, or all of them are negative. So, this is a complete characterization of completely mixed matrix game. Let me repeat what I am saying. A game is completely mixed, a matrix of this type, m cross n, where m rows and n columns. I am assuming the value of the game is 0, the minimax value. Then in that case, the game is completely mixed if and only if it has to be a square matrix, the rank of the matrix is n minus 1, and all the cofactors are either all of them are positive or all of them are negative. It is a set of necessary and sufficient condition. This is the result of Kaplansky. Let me give you some examples where this is satisfied. That is important.
Mr. Bhattacharya, can you have a completely mixed game with B non-zero?
Yeah, you can have. You can have. Yes, no problem. That is, you add a positive number to such thing, to every one of them. It won't change.
But then the characterization will also...
No, this is for only this V equal to 0. Okay. But you can make some, that is, you can compute the value of such a game, okay, with the help of this. Okay. Let me give you a class of games for which this V equal to 0 is satisfied. That is your question actually. Are there, how do you identify it? One of the identification is, take a matrix A which is Skew-symmetric like this, which is A equal to minus A transpose. Such matrices are called Skew-symmetric matrices. Skew-symmetric matrices have some special property. There is a very beautiful result of David Gale, but he has written a very nice book also way back in 1960, Theory of Linear Economic Models. He has shown when the matrix is skew-symmetric, value is 0. So, all skew-symmetric matrices will have value 0, at least in that situation this result can be applied. Okay? Yes. I am just giving you an example. The skew-symmetric matrices also have some interesting property. One of them is, if the skew-symmetric matrix is of odd order, say 3 by 3 or 5 by 5 or 7 by 7, then the determinantal value of that is always 0. Okay, let me say. If n is odd, determinant of A is 0. You can easily verify because you just change the sign minus 1 power that odd, so the value of the, I mean one can check this. When it is odd, the determinant has to be 0. When it is Skew-symmetric, when it is even, there is also a nice result. When n is even, the determinant of A is not only non-negative, also it is the square of a polynomial. The elements of the polynomial comes from the elements of A. That is, for example, I mean, let me give a very simple example. 0 A minus A. This is Skew-symmetric of order n is equal to 2. So, here determinant A equal to A square, and you can verify it for 4 by 4 etc. Okay. Now, one of the questions which Kaplansky left open in this particular paper was, it is clear that when you have a skew-symmetric matrix of even order, for example, take let n is of the form 2m, A is minus A transpose. Such a game can never be completely mixed because of this result. Because we know that when the game is skew-symmetric, the value is 0, this is automatically satisfied. If it has to be completely mixed, the rank should be just 1 less than that. So, when you go down in the order, it will be an odd order, and the determinant of that is 0 by that remark I made there. So, in other words, when you have a skew-symmetric matrix of odd order, such a game can never be completely mixed. Okay, such games. So, you left open this problem. If n is equal to 2m plus 1, can you give some kind of a better characterization, or rather a different characterization compared to this? Because when n is even, such game can never be completely mixed, but when n is odd, can you do that? So, that is the thing which he takes up after 50 years, and this paper appears in linear algebra and its application. I will just quote the result of that paper. That is where the student, takes up this problem. So, let me state that result. This is again Kaplansky. Assume A equal to minus A transpose, n is of the form 2m plus 1 theorem. Then the game associated with such a matrix is completely mixed if and only if, I am just going to write down something, I will explain this, P1, P2, etc., Pn, P1 are all different from 0, and they alternate in sign, and P1 minus P2 etc. minus Pn is proportional to the unique optimum. So, let me explain this. See, I have a skew-symmetric matrix of odd order, and such a game is completely mixed if these n conditions are satisfied. That is, these are things which I have not defined, I will define it shortly. They are all different from 0, these n thing, and not only that, if P1 is positive, P2 is negative, P3 is positive, etc. If P1 is negative, P2 has to be positive, etc. And this vector is proportional to the unique optimal strategy of a completely mixed game. What are these PIs? The PIs are the Pfaffians. This is something which is nice because he connects it with what is a Pfaffian? I will go with starting with a 2 by 2, 0 A minus A. I will define Pf of A to be simply the element A. Okay. What about when I go to 4 by 4? For instance, because I just do that also for 4 by 4. Zero A B C 0 D E 0 F 0. I don't write the below line because it is the negative of that, because it is a skew-symmetric. So, Pf of A is simply AF minus BE plus CD. So, that is the way it is defined. Not only that, the determinantal value of A is simply the square of this. Determinant of A is Pf of A the square. I said that it is a square of a polynomial. The polynomial which appears there is called the Pfaffian. Okay, so that is the thing. Of course, the definition of Pf of A can be defined, but it is technical. I will just leave it as it is. Okay. Yeah, please go ahead.
Your n is 2m plus 1.
What do you say?
So your n is 2m plus
That is true, because I am defining it for the, because I have to tell you that the Pfaffian, these are principal Pfaffians. That is, I will omit one row and the corresponding column and then look at the Pfaffian, because I have not yet defined what are these PIs. Okay. This P1 is the Pfaffian of the given odd order matrix. You just leave out the first row and the first column, that is of even order. I demand that the determinant of that should be positive. So, I take the square root of that. So, this P1 could be either positive or negative, but it is done in a particular way so that the sign is fixed. Okay. So, that is how I do it. Yeah, your question is a very valid question, but so these are called principal Pfaffians. So, his result is remarkable in the sense that it is enough if you verify these n conditions rather than all the cofactors in the general case. Okay. So, that is that result he proves it in 50 years later. That, okay. Now, what is the one of the questions which in the case of Nash, I am going to define what is called a bimatrix game. So, I have two matrices A comma B. Assume that these are of order m cross n and m cross k. Of course, maybe I can give some examples so that it will be clear. See, there are two prisoners. I mean, this is what is called the prisoner's dilemma. Most of you might have heard this. These are not zero sum, non-zero sum games. So, here each prisoner can confess or lie. This is the payoff matrix corresponding to the prisoner 1, P1. Here I have the another matrix with reference to the prisoner 2. If both confess, each one gets 5 years of rigorous imprisonment. If prisoner 1 confesses, prisoner 2 lies, he gets away free and he gets 10 years. And similarly, if prisoner 1 lies, he confesses, then prisoner 1 gets 10 years. Otherwise, say this is the thing. These are not zero sum, because see, in the usual matrix game, you define only the payoff of one person. For the other one, it is the negative of each entry. But here, so this is the kind of matrices I am going to look at. These are called bimatrix game. These were first introduced by John Nash and he wrote a very short thesis and he published a series of papers. The one I am referring to is which appeared in Annals of Mathematics 1951. He proves what is called the concept of equilibrium point. Here what do you do? Are you going to confess or not? You can communicate, does not matter. See, here the best strategy is to confess. Both of them should confess. Suppose he confesses, and if he lies, he is going to get more punishment. But here, if both of them lie, then both of them get less punishment. But then I may tell you that I may lie, but later I may change my mind when I was actually interrogated. Then you will get more punishment. Suppose I confess and you lie, you get 10 years of rigorous imprisonment. Here the only unique equilibrium point in the sense of Nash is confess, confess. That is, each one of them must confess. That is the best strategy. So let me define now the notion of an equilibrium point here. Call a pair of strategies probability vectors x0 for player 1 and y0 for player 2. X0 will have m coordinates and y0 will have n coordinates. These are all probability vectors. A Nash equilibrium point, if, see, either you can assume that both want to maximize or both want to minimize. In this case, both would like to minimize, okay, that is the thing. But there are some problems where if both look at the profits of each thing, then they may want to maximize. So, I will use the notation accordingly. Equilibrium point for the maximum problem if x0 transpose A y0 is greater than or equal to x transpose A y0 and x0 transpose B y0 is greater than or equal to x0 transpose B y for all x and y. X and y are probability vectors in the corresponding. See, what it means is, if player 2 uses x y0, both of them want to maximize their expected income or whatever you want to say. If player 2 uses y0, there is no incentive for player 1 to deviate from x0, because already that gives him the maximum, because it is greater than or equal to for all x. And similarly, if player 1 uses x0, then there is no incentive for player 1 to change from y0, because that is already giving this. Such a pair of vectors is called an equilibrium point in the sense of Nash. Of course, it generalizes the notion of optimal strategies in the matrix game. Okay, such a point is and we say the bimatrix game is completely mixed if both these strategies are completely mixed. If every equilibrium point is complete, I mean natural generalization. See, in all the problems there are two extremes. One is checking whether there is a unique, I mean, let me say in the case of the,
one quick question.
Yeah, please.
I'm not understanding this meaning of equilibrium, because you are allowing the confessions to change, you are allowing the decision to become
Sure.
dynamic. So what is the meaning of, like 3 is the minimum, and you said that...
Okay, how do you get 3? Only if both of them lie.
Right.
Suppose I change to confession.
So that's what I'm saying.
Yeah, so here there is no, I mean this point is not an equilibrium point, because I can do better by confessing.
So that's what I'm saying,
Yeah.
that today I say something, divulge some data, and tomorrow I change the data. As a result of that, the decision also changes. Then what is the meaning of equilibrium?
No, equilibrium is, see, if one person deviates, the other one should not gain. Okay, that's what I am saying. See, the idea is, here let me tell you something here. You come back here, because everything you are going to turn in terms of the numbers. See, here what it says is, against y0, x0 is the best reply. And similarly, against x0, y0 is the best reply. Suppose he uses this, L, then my best reply will be C. Then you will be punished. No, you understand what I am saying? Suppose he chooses this strategy, that is the second column. Naturally, if he also chooses the second column, both will get 3. But he may do this one. This is the best reply against that. L L is not the best reply. That's what I'm saying. That is, he can do a better job by punishing the other person. Okay. So that's the equilibrium notion. Now the question is, I mean, here when you have a matrix of this type, see, the notion of equilibrium is a little bit complicated. There are two extreme cases which are analyzed. In fact, people who work in computer science are interested. One is the following. One, does there exist a pure equilibrium? Maybe I will explain what I mean by a pure equilibrium with reference to this example, that will be clear. This is a minimization problem. So, call a pair I naught J naught pure equilibrium, I mean with reference to this example, if A I naught J naught is less than or equal to A I J naught and B I naught J naught is less than or equal to B I naught J for all I and J for all I. Here the pure equilibrium is this one, 1 1. 1 1 is the only pure equilibrium. This, the other one cannot be a pure equilibrium. 2 2 cannot be a pure equilibrium. You can check this condition. That is, again J naught, I naught is the best reply, and against I naught, J naught is the best reply. So such a thing is called a pure equilibrium. Now, in other words, the one, does there exist a pure equilibrium, and can you check this, and can one check in polynomial steps? Two, does, I mean, is every equilibrium completely mixed? These are the two questions. One is these are the two extreme cases. One is the pure, the other one is every equilibrium is completely mixed. This can be done. I don't need to know even the entries of the matrix. I will ask the question. I will take the first one. Suppose I have the A11 is greater than or equal to AI1 for all I. I will ask my friend or opponent, is it an equilibrium? He will look at his entries and then tell. That is, if B11 is greater than or equal to B1J for all J, then he will say yes. He has to say yes or no, nothing else. So that way I have to check each one of the entries. So there are only mn entries. So I will do it in mn steps. So it can be done in polynomial time. The question here is not as easy as in the case of the matrix game. I don't think, I mean, till now no polynomial algorithm is possible to check whether a given pair of bimatrix game is completely mixed. So that is the problem which the student looks at. And let me tell you what the answers she got. That is, in other words, she was trying to see whether result of Kaplansky can be shown in the case of the bimatrix game. So that's the student's name is, let me say that, Vasudha Sharma. She submitted in 2019 June. That is for her MS thesis. What she has shown is the following. And before that, I have to tell you a result of my good friend Raghavan. That this result she makes use of. This appeared in 1970, London Mathematical Society. He has shown among other results the following. If a bimatrix game A comma B is completely mixed, then it has a unique completely mixed equilibrium. That is, if you are told that the given game is completely mixed, then there is only one equilibrium for the entire game, bimatrix game, and it has to be completely mixed. So that's the result which he has shown. Okay. So what I mean, let me tell you what she has done it. Take the, so she is taking a 3 by 3 matrix with the following sign structure: 0 plus minus, minus plus, 0 plus, minus plus. This is my sign structure of A. The entries could be anything except that A is equal to minus A transpose. Okay. If this is positive, if it is A, this is minus A. So with that, A is equal to minus A, 3 by 3. B also, but B sign structure is completely the opposite: 0 minus plus, plus 0 minus, minus plus, I am sorry, here this is 0. I mean, B is not equal to A, please remember that A is not equal to, need not be, it can be but it need not be, and B is equal to minus B transpose. The result which he shows is the pair A comma B is completely mixed. That is the result. That is, you have a 3 by 3, remember 3 by 3 is Skew-symmetric matrix, both of them. The sign of this is this, and B is just the opposite of every one of them. A need not be equal to B, remember. Of course, if A is equal to, what I am saying is B is not equal to minus A, let me put it that way. B is not equal to minus A, that is the important thing. If B is equal to minus A, then this becomes a zero sum game. Already that result, already analyzed by Kaplansky in general, so we don't have to do anything. So B in general will not be equal to minus A. It is not zero sum, let me say that. The result which he shows is, in this case, the pair A comma B will have only one equilibrium point and both of them are completely mixed. So that is the result. What happens when you go to higher dimension? That is the next thing which she wanted to answer. So what she looks at is the following. There are two things which is happening here. If you look at this matrix, the P1 is positive, because that is this entry. This is P1 is P1 is omitting the first row and the first column, that is positive. P2 is negative, because P2 means omit the first row, second column. So the Pfaffian of this 0 minus A plus is this, the sign of that, which is negative. And what about P3? P3 is again positive. Okay. Now let us look at here. It is just the reverse. Let me call the Pfaffian of this as Q1. Q1 is negative, Q2 is positive, Q3 is negative. So from this it is clear that by the result of Kaplansky, the second paper, this game as a zero sum game is completely mixed, because that is the result which he has shown. That is the matrix must be skew symmetric and it should be of odd order, and the principal Pfaffians must alternate in sign. So here it does. So this game as a zero sum game is completely mixed. This game as a zero sum game is also completely mixed, because here also these are Pfaffians of the second matrix B. What she proves is, in such a situation, the bimatrix game itself is completely mixed. It is if and only if. Okay, that's the result. Now, when you go to the higher dimension, what do you do? Can you carry out this thing? In other words, suppose I take a 5 by 5 matrix. By 5. Same things, the signs are going to be like this. Okay? But in addition, you assume this. P1 is positive, P2 is negative. The individual games have to be. and P phi is positive, and Q1 is negative, Q2 is positive, Q phi is negative. So, suppose you impose this condition like here, because this condition you have to impose when you go to 5 by 5, because you have to look at the determinant of order 4 by 4, in which case the Pfaffian is constructed in a particular way. Okay. But you have to make that assumption, P1 is positive, P2 is negative, etc. Does it imply the bimatrix game A comma B is completely mixed? The answer is no. A B need not be completely mixed. So, that is what is happening. So, even when you go to 5 by 5 with the same assumption as here in the 3 by 3, if you take it out, I mean these assumptions you have to make it, P1, P2, etc., everything, and A, B need not be, she gives a counter example to that.
Is it possible to have a suboptimal solution?
What do you say?
Suboptimal solution.
Suboptimal means what exactly mean?
Not the full 5 by 5 matrix, but you can have a lower dimensional matrix embedded, which will give equilibrium.
No, this has an equilibrium. About that there is no question. I mean, this 5 by 5 matrix has a completely mixed equilibrium.
Oh.
That is not a problem. The problem is whether every equilibrium is completely mixed. That's the question. Okay, because see, as soon as you put this condition by Kaplansky, individually they are completely mixed. So, you can use that and get a completely mixed equilibrium. That is not a problem. The problem is whether every equilibrium is completely mixed. That need not be. So, that is the, because here what happens is she gives an example in which not only there exists a completely mixed equilibrium by Kaplansky's result, I mean individually, that you can use it, get a completely mixed equilibrium, there is also a pure equilibrium, both in that example. Because I have to write the number, but I am not writing. I mean, those of you who are interested, I can show you those numbers.
In Raghavan's paper, he didn't mention skew-symmetric.
What do you say?
In Raghavan's paper.
No, he doesn't. No, he just talks about, he assumes the game is completely mixed and then proceeds. That is the easy part. The part is given, even the individual games are completely mixed in the sense of Kaplansky, can we say the bimatrix game is completely mixed? So, that seems to be a hard problem. I have no answer except for this simple question of 3 by 3. For 5 by 5 it does not go through. What are the additional conditions you have to impose? I do not know. I think I will probably stop here. That is the